So the first one is from a carbonate fractured reservoir offshore Brazil. And let's try to show you some of the main topics we touched. So the context, we have a post-salt Albian carbonate reservoir offshore Brazil. The structural area, the study area is a structural high. It's quite simple. It's structural high bounded by major faults with kind of polygons faults, you know. And the facies are typical of carbonate banks. The goal was to study the existence and impact of the fractures network with, and this is challenging, relatively few BHI, relatively few borehole images and core pictures, seismic attributes, and but we have a significant amount of well test. So the static data, just to have a quick look, we had the core data for 11 vertical wells for a total length for more or less 1 kilometer. Of course, we didn't touch physically the cores because of the sanitary situation, so we have looked just to some pictures. And this is quite a big limitation anyway, as Thomas showed a few minutes ago. Surely to have a look direct to the cores, given information really rich than just to see some pictures. But anyway, we had BHI for 3 deviated wells and 2 vertical wells. So as you can see, the database from a static point of view was relatively limited. It is not a big database. We had surely a reservoir grid, and finally a seismic with 3D faults and seismic attributes. So what about the core analysis? Core analysis, as shown a few minutes ago, is a quite important step of the fracture characterization, because it's the only way to touch, to see really hard data like fractures, like every elements, still lights, as you were talking about a few minutes ago, or artifacts and so on. Also by picture, sometimes it's possible to get some information, surely, even if they are, the uncertainties is higher. Anyway, this here we have 2 examples of pictures, so coming from this course, and as you can see, we have we observed some fractures of possible tectonic origin. They look like open, without a total cementation. Sometimes they are, we have some example as well of fractures cemented by calcite or quartz. It depends on the lithology around, you know. And we had also some diagenetic fractures. I don't want to go in details, but this kind of fractures usually they are cemented. They are early in the related to the compaction phenomena, and usually this kind of small features like sterilites as well do not, or let's say, are not likely to participate strongly to the fluid flow. Tectonic features like the few examples I show in this slide potentially can affect the fluid flow, because they can be kept open also in depth. So the conclusion of the core data analysis were that yes, we have fractures probably of tectonic origin. The core recovery is quite low for some wells, which suggests that maybe we have some fracture at the cores, even if this information is quite I mean, weak. And we have some mostly diagenetic cemented fractures, but we have also some tectonic cemented or semi-open fractures. And we have also maybe a weak relationships with the distance to the faults, like shown this in this map, where we can see that the red triangle, which corresponds to a well with evidence of fracturing, is located exactly, in the proximity of a fault, for major faults, and other wells with the green color are far from the major faults, but it's just a weak information. It doesn't work. Okay, so let's go to the BHI analysis, borehole images. And this is a very important tool for the fracture analysis, because it's the only way to get information about the density and the orientations. Because as you know, probably know, the cores usually are not oriented. So we can get information about the type of fractures, about the cementation state, which are very, very important parameters, but we cannot get information about the orientations and density of fractures, which also are very important parameters for the fracture modeling. So really we need this kind of data as borehole images and so on. So here we had 5 wells with borehole images. As you can see, the BHI quality was quite low in all the cases, unfortunately. But anyway, we were able to interpret it, a lot of some fractures and elements. In these pictures, the black tadpole correspond to the bedding. So the fractures are the colored tadpole in red, blue, green colors, depending on different type of fractures we could interpret. Anyway, this is just an example, just to show us this kind of information is really fundamental, as I told you a few minutes ago, to get the density along the well and the orientation, because don't forget that each tadpole, the position of each tadpole, which are the small point with the little q in the figures, correspond to a specific orientation, a deep azimuth and a dip of angle for each fracture. So this kind of data can be analyzed from a statistical point of view by a specific software like FracaFlow. So when we load these elements in FracaFlow, we can create this kind of diagram, or of stereo diagrams, like a strike diagram or a Schmidt stereo diagram. Anyway, they tell the same. The first diagram represents the pole of the fractures, and the second diagram, the strike one, represent the direction of fractures. So they are corresponding. I mean, they tell us the same. And this kind of visualization allow us to define the families of fractures. For example, a quick analysis that we performed, a first conclusion, if you want, of the study was, okay, the dispersion of the strikes of the fractures is really high. I cannot define 1 or 2 major families, but when I show each wells in a map with the main strike orientation, the first observation we can make is that the direction of fractures is, in most of the cases, more or less parallel to the nearest faults. So even if the general strike look like highly dispersed, when we look at the specific wells in the specific location in the map, it's quite clear that most of the fractures parallel to the faults. This is a quite important information, because it's a first suggestions that maybe the fractures I'm looking for, I needed for, are related to the faults and not just the regional background fracturing. But let's say what happens before or after. This map is just to show the density, the average density of the tonic fractures in the 5 study wells with respect to the location of the faults. It's another piece of information, because we can say that the 2 wells showing the highest fracture densities are located to A major faults. So the 2 fractures with the 2 density 0.80 and 0.35, they are the most fractured. They are close to the A major faults. So there are several pieces of information. Each one is quite weak alone, but when you create, the puzzle, we can put everything in the same study, we can extrapolate and maybe get some information about the distribution of the fractures in this field. Another piece of information very important is in general, in every fracture study, is the seismic. In particular, we work with the seismic attributes, and we have a specific workflow to produce by computing several, by adding several seismic attributes, like we are talking about the geometrical attributes like similarity, dip, edge, and so on, curvature as well. We can produce this kind of fracturing index map, which tell us about the probability to have a fracture area in the field. So this kind of information is quite important, because this kind of information give us information, let's say, about what happens between wells, because the core information and the BHI information is along the wells, so it's a point. It's a very hard datum maybe, but it's really located at the well, around the well. When we would like to extrapolate to understand what happens between wells, we need the seismic. So in this study, unfortunately, the quality of the seismic attributes was not so high, so the results have quite big uncertainties, but the interpretation was performed, and at the end of the day, we had this kind of lineaments in a black color in the figures, which were added to the red color faults, which are the big faults, the big seismic faults bounding the structure. So this kind of maps should be to the final model to provide the permeability to the system. Another important step, I don't go to the details, but just a few slides, where the analysis of dynamic data. As I told you, in this study, we had a quite beautiful, quite big. But it was really very interesting to I don't know if, can you hear me? I have maybe some problem.
Yes, we lost you just a few seconds, but it looks like you're good now.
Okay.
It's fine, it's fine.
Because I just saw some message. So, okay. So the study was interesting from a dynamic point of view, because we had a quite beautiful database about transient well test. In particular, we performed the analysis of 30 transient well tests. And well tests are very interesting from a dynamic point of view, because they provide they suggest about the performances of the fractures in the reservoir. The question is, the fractures I saw in the static analysis from CORS, FMI, Seismic, do they participate to the full flow or not? So this question is very crucial, because I have to put in the model only the object that provides a possible or probable or potential impact on the fluid flow, and not the object that cannot provide this fluid flow. So the main conclusion were that in no clear dual porosity signature was detected. So it means that the presence of a well-connected fracture network is not clear, which means, in other words, that probably we don't have a connected network of what we call diffuse fractures around the wells, around the field. On the other hand, most of the well, 80% of the wells, exhibit a negative skin, and the most typical well test signature is fracture with finite or infinite conductivity. In other words, this suggests that we have fractures, we can have some fractures crossing the wells, but probably these fractures do not constitute a network really connected in all the reservoir, in all the field. We can really play with dynamic data as well. We can analyze also PLT, other kind of data, and so on. But one of the major input for the fracture modeling is the estimation of the KH. Thomas showed us a few minutes ago how we can calibrate the model with the KH estimation. So you understand that how much is important this estimation if we want to calibrate the model, if we want to put a conductivity value which is not completely crazy to our model. So it's why we really want to analyze, we put attention to this kind of analysis. We can also put in a graph, like in these figures, in the slide, we can put the KH from well test and the KH calculated or computed or estimated from the matrix, and to put them in the same graph. What happens that in a not fractured reservoir, the ratio between this kind of KH should be 1. I mean, all the production of the well, let's say very simple, all the production of the well is performed by the matrix. But if the KH test is much higher than the KH matrix, we can suppose and suggest that another parameter play a crucial role on the dynamic of fluid flow, and in this case it should be the fractures. So it's why all the well in which the ratio is higher than 10 are very probably fractured. Wells with a KH ratio of about, let's say, between 3 and 5 should be fractured. And of course, wells in which the KH ratio is 1 or less than 1, they are not likely to be fractured. It's quite simple as analysis. So in this field, we have a behavior quite typical of the fracture reservoir. And this behavior is the very high heterogeneities of this ratio. We have wells with a really high KH ratio, and you have a well with a values of 1, which means that we have some wells which are probably fractured, and we have some wells which are probably not fractured. Another analysis we can perform is to put the KH ratio against the distance to the fault. This graph is not maybe conclusive, but suggests that all the wells, most of the wells with the KH ratio higher than 10 are located, so I mean probably, highly probably fractured, are located at a distance less than 100 meters away from lineaments, tectonic lineaments or faults. The conclusion is quite simple. I don't see a clear effect of diffuse fracture in the field, but it's quite clear that the faults and lineament play a major role on the behavior of the wells, of the behavior of the KH, more than the observation coming from the static point of view. So we can also extrapolate, or at least estimate the zone of influence, if you want, the damaged zone around the lineaments and the faults, which was estimated at around 50-75 meters on each side of lineaments, and up to 100 or maybe 200 meters away from the major faults. Putting all this observation from static and from a dynamic observation in the same network, we can build up a conceptual model for the fracture distribution in the field. And which is visualized really in a quite simple manner in this way in this slide. We have, so in our field, we observe the fractures, yes. We observe that most of the fractures are located or at least impact the behavior around the faults. In other words, within the area that are called usually damaged zone, fault damaged zones. We have also lineaments, which are small faults or maybe fracture corridors, and also around these lineaments we have some impacts, so we put fractures. And as a background, we can have some diffuse fractures, but let's say these fractures are probably not connected. So in the little zoom, in the bottom part of figures, you can see that the fractures are, we can put with the FracaFlow, with the software, fractures, but we try to make these fractures not connected to avoid this kind of general connecting behavior that are not being observed in this field. Once the conceptual model is ready, we try to generate or to reproduce it, if you want, in the FracaFlow software. So this is the second step of the FracaFlow utilization, because the first step was the analysis of the data, of course, the definition of the families, of the densities, of the faults, and so on. And now the second step, really the second utilization, is the modeling. So FracaFlow allows, as you know, to model every, let's say, every type of fracture types, of fracture kinds, like big faults, smallest faults, and diffuse fractures. So here we have just a few pictures from the DFN generation, and we have, as you can see, the 3D seismic faults, which are 3D objects. We have lineaments coming from the seismic attribute seismic interpretation, and if we have a look zooming in, we can see that around the lineaments or around the faults we have fractures parallel to these big objects that are the fault-related fractures, and we have also, as I told you, a background diffuse fracturing without a complete or total connectivity, so I mean with a very low connectivity. So these are the different elements constituting what we call the DFN, the Discrete Fracture Model, associated to this specific field. An important step, as Thomas showed us a few minutes ago, is the calibration, which take into account the KH coming from the well test analysis. In other words, we try to calibrate the conductivity of the different fractures in our model, faults, lineament, fractures, blah blah, calibrate them to have a conductivity close or near or similar to conductivity calculated from the well test. So the specific values we try to calibrate is the KH. So this is an automatical computation by FracaFlow, but really we can play with different parameters, with different conductivities, and with different families of fractures, faults, lineament orientation, and so on. So it's automatical, but it's really not just push a button, you know, it's an iterative process that can be quite difficult sometimes, but I think that it can not only calibrate our model, but also give us some information about the fractures performances. Like in this example, for example, when we calibrate the different objects, we can also create this kind of map in which you can, for each wells, we can estimate the contribution of fractures. As you can see, the black color, the black circle, or the very dark color circle, correspond to those wells in which by the calibration tool, we estimate we state a very high fracture contribution based on the KH estimation, of course. For other wells in green color or in yellow color, the contribution of fracture is really very low. If you look at this map, you can really understand that most of the fractured wells are located close to the big faults. So the conceptual model works, and we were able to reproduce more or less this conceptual model in the software, which was our aim of the game. So the final step of the fracture model is the computation of the equivalent fracture properties. In other words, which is called in the software the upscaling process, but it's really the computation of the properties of fractures for each cells of the model. And what is nice, I think, with this FracaFlow is that we can also, once the model is more or less ready, we can play with different parameters to take into account the uncertainties in a quite quick way. In this example, for example, we created the different cases, a low case, a base case, and a high case, in which you can see that we vary just the parameters related, associated to the different families of fractures. Just an example, in the base case, we have, of course, faults, lineaments. We have fault-related fractures around the 100 meters on each side of the faults, and have some diffuse fractures. As the uncertainty of non-fracture distribution is quite high, we create also low case, in which we do not put any diffuse fractures, and we reduce the fault-related fracture occurrence to only 50 meters. And finally, we perform also on high cases, in which a very optimistic case, if you want, in which we put as well fault lineaments, but we increase the impact of the fractures related to the faults, and we increase also the impact of the fracture related to the lineaments, and we also increase a little the diffuse fracture. So it's just an example, a real case, just to show you how it's quite easy, once the conceptual model has been created, to vary the different parameters to take into account some uncertainties on the final model.